August 6, 1944, somewhere over Eastern Europe. Lieutenant Hollis Nowlin gripped his control stick as his P-51 Mustang screamed through the sky. Below the wings of his fighter, the patchwork of European fields and forests blurred into an indistinct, fast-moving canvas of summer greens and browns. The air at this altitude was thin and cold, but inside his cramped cockpit, Nowlin felt the heavy beads of sweat building under his flight suit. Ahead in the distance, a Messerschmitt Bf-1's R09 was running for its life, desperate to escape the pursuing American fighter. The German pilot was Gunter Schack, a seasoned Luftwaffe ace who had survived countless dogfights on both the eastern and western fronts during the war. He was no ordinary pilot. Schack had earned his reputation through years of brutal aerial combat against Soviet and American adversaries alike. He had learned to respect American fighters, but he had also learned their limits and weaknesses through hard experience over the years. He knew exactly how fast a Mustang could fly, how quickly it could climb, and precisely how to escape when the odds turned against him. These calculations had saved his life dozens of times before, but on this specific day, none of that hard-earned knowledge would save him. Nowlin pushed his throttle forward, and his Packard Merlin engine responded with a surge of power that defied everything Schack thought he knew. The distance between the two fighters shrank with terrifying speed as the American plane closed in on its prey like a hungry hawk. Schack twisted his head to check his six, and what he saw behind him made his blood run totally cold in his veins instantly. The Mustang was closing at a rate that seemed physically impossible for any piston-engine aircraft to achieve in 1944. It was as if the American had discovered some dark secret that completely rewrote the laws of physics right before his eyes. In the cockpit of his P-51 aimed Hell's Bell and watched his airspeed indicator climb past numbers that represented the edge. His engine was drinking a new experimental fuel designated simply as Grade 150, which transformed the fighter into a demon. The engine sang with a power that seemed almost supernatural as Nowlin squeezed his trigger to unleash a deadly volley of fire. Tracers lanced through the sky and tore into SC Hack's Messerschmitt with brutal efficiency, ripping through metal and fabric alike. The German's cooling system ruptured immediately, spraying hot like all across his windscreen, like blood gushing from a mortal wound. His engine temperature began climbing toward critical levels as red warning lights flickered frantically across his instrument panel. The fight was over before Schack could even respond properly to the attack, but then something truly unexpected happened. Instead of finishing his crippled opponent with a final burst, the American pilot pulled away and ceased his attack. Nowlin was running dangerously low on fuel and ammunition after a long escort mission to Soviet air bases for Operation Frantic. The grueling mission had taken him all the way across occupied Europe, and he needed to return to base immediately. He waggled his wings in a gesture that Schack would remember for the next 4 decades, then turned his Mustang back. Schack nursed his damaged fighter toward the ground, smoke trailing from his engine cowling in a dark ribbon against the sky. He managed to belly land near German lines, the aircraft scraping across the field in a shower of dirt and sparks. He climbed from his cockpit, shaken but alive, his hands trembling as he stood on the solid ground once again. As he watched his aircraft burn, black smoke rising into the clear European sky, one single question consumed his thoughts. How had the American closed so quickly a demonstrated performance that exceeded anything Schack had ever encountered in combat? For 40 years, Gunter Schack would carry that question with him, never understanding why the American had spared his life that day. He assumed it was an act of chivalry or exhaustion until historians connected the two pilots decades later and the truth emerged. Nowlin had believed his burst had merely damaged rather than destroyed the German fighter, having no idea it was fatally wounded. But the larger mystery of how an American Mustang had demonstrated such impossible performance actually had a much simpler answer. It was an answer that lay not in superior airframe design or brilliant piloting, but in something far more mundane and overlooked. It came in 55-gallon drums painted olive drab and smelled of Tetratil lid, because the secret was simply the fuel. It was aviation gasoline, and its story would reveal one of the most overlooked technological advantages of the Second World War. To understand how American fighters transformed from capable adversaries into unstoppable predators, we must travel back in time. We must go to a test facility in Ohio where military engineers were about to witness something remarkable that changed warfare. Early 1940, at Wright Field in Dayton, a test pilot steadied his hand on the throttle of a P-51 Mustang. As he pushed past the Standard War emergency power setting, he entered dangerous territory where catastrophic failure was a real possibility. Operating an aircraft engine beyond its rated limits could result in pistons shattering or connecting rods breaking under the immense stress. But the engineers had assured him that something fundamental had changed, and the engine roared as boost pressure climbed higher. The manifold pressure gauge climbed to 75 inches of mercury, far beyond what had previously been considered safe for operation. The aircraft was being fed by a new experimental fuel designated simply as Grade 150, developed in secret by petroleum chemists. At 25,000 feet, the Mustang accelerated through 448 miles per hour, smashing previous speed records. The test engineers on the ground exchanged stunned glances as the radio crackled with the pilot's unbelievable report from above. They had expected improvements based on the chemistry, but what they were witnessing exceeded their most optimistic projections by far. This was not merely improvement, nor an incremental gain. This was a total transformation wrapped in purple-dyed aviation gasoline. A chemical advantage so profound that it would render obsolete every assumption the Luftwaffe held about American fighter capabilities. The numbers being recorded would rewrite the tactical manuals of aerial combat, and the numbers told the story with brutal clarity. A P-51 Mustang running on standard grade 130 fuel could reach 437 miles per hour at 25,000 feet. This was already impressive performance, but the same aircraft running on grade 150 fuel could exceed 448 miles per hour. 11 miles per hour might not sound dramatic to civilian observers, but in the mathematics of fighter warfare, it represented the vital difference. It represented the difference between hunter and hunted, between prey, and ultimately, the difference between life and death. Consider the implications from a German perspective, as the Messerschmitt Bf-1's Aero 9G was the Luftwaffe's primary frontline fighter. This aircraft had been the backbone of German air power since the early days, having a maximum speed of 400 miles per hour. The Focke-Wulf 190A was a newer and in many ways superior design that could reach 408 miles per hour under optimal conditions. Against Mustangs running standard grade 130 fuel, German pilots could at least attempt engagement on favorable terms. They could dive away using gravity to build speed to escape, or execute slashing attacks at high speed, relying on initial velocity. These tactics came from years of combat, but against Mustangs running grade 150 fuel, none of them worked anymore. German fighters were operating at a disadvantage that no amount of pilot skill or tactical brilliance could ever hope to overcome. The Americans had changed the rules of the game without building a single new aircraft, just by changing the liquid in the tanks. Every Mustang in the inventory was suddenly faster than specifications suggested, transforming the fleet into superior machines. What the Luftwaffe did not know was that Allied chemists achieved something the Third Reich's synthetic program could never match. German fighters struggled with B for fuel rated at 91 octane, while their best fuel barely matched Allied grade 130. American refineries were producing aviation gasoline with a performance number of 150, which seemed truly impossible. To understand this advantage, we must examine what octane ratings measure and why they matter so critically for aircraft performance. Every piston engine operates on a principle where air and fuel mix in a cylinder, creating a volatile mixture ready for combustion. A piston compresses this mixture, increasing pressure until a spark plug fires, igniting the mixture at the precise moment. The resulting controlled explosion drives the piston downward with tremendous force, but the critical word here is controlled. If the fuel ignites spontaneously before the spark plug fires, the result is detonation instead of a smooth, even burn. You get an uncontrolled explosion that creates shockwaves inside the cylinder, hammering against the piston and cylinder walls. Sustained detonation will destroy an engine in seconds, tearing metal apart and potentially killing the pilot instantly. Octane ratings measure exactly how much compression a fuel can withstand before spontaneous detonation actually occurs. A fuel with a performance number of 150 meant it could withstand 50% more compression than iso-octane. Higher compression ratios allow engines to extract significantly more power from each individual combustion cycle efficiently. More power means faster aircraft and higher ceilings, and the development of high-octane fuel began in American labs. Started during the 1930s, driven in part by a visionary Army Air Corps officer named Jimmy Doolittle, before he became famous for leading the daring 1940 raid on Tokyo, which boosted American morale hugely. Doolittle had earned a doctorate in aeronautical engineering from MIT, making him unique among his peers in the service. He was not merely a skilled pilot, but a trained scientist who approached complex problems with rigorous mathematical logic. He understood clearly that the future of air power depended not just on aircraft design, but critically on the fuel itself. Throughout the 1930s, Doolittle worked tirelessly to convince the military and petroleum industry to invest heavily. His efforts faced considerable resistance, as producing high-octane fuel was expensive, complex, and seemingly unnecessary then. Events would prove Doolittle spectacularly correct when war finally erupted and the need for speed became the only priority. In 1940, when war was raging in Europe, American fuel production centered on 87-octane gasoline production. This was woefully insufficient for high-performance combat aircraft, and the British were desperate for any advantage to survive. After the fall of France, they worked frantically with American oil companies to develop 100-octane fuel for fighters. This new fuel became available just in time for the Battle of Britain, but its impact on the air war was immediate and profound. British Spitfires and Hurricanes using the new fuel suddenly had 30 to 40 miles per hour more speed at altitude. Their climb rates increased by 500 to 1,000 feet per minute, giving them a critical tactical edge in combat. German pilots who had previously enjoyed performance advantages suddenly found themselves fighting on even terms or worse. Many Luftwaffe veterans who survived the Battle of Britain would recall the puzzling improvements in British fighter performance. By 1940, Grade 130 fuel had become the backbone of Allied air power thanks to engineer Eugene Houdry. French émigré engineer Eugene Houdry had perfected the catalytic cracking process that made high-octane fuel production viable. American refineries adopted his techniques, and by 1943, 17 plants were producing high-octane gasoline. American refineries churned out millions of gallons monthly, while German production remained permanently bottlenecked by coal. Germany had vast coal reserves but limited petroleum access, so they used the Burgess process to convert coal into gasoline. This process was technically sound but slow and extraordinarily resource-intensive, requiring massive industrial facilities. Their premium C3 fuel was roughly equivalent to Allied grade 130 fuel, but available in far more limited quantities. German synthetic fuel plants at their peak produced roughly 90,000 tons of aviation fuel per month, which was not enough. American refineries produced several times that amount, creating a logistical tidal wave that eventually drowned the Luftwaffe. The introduction of Grade 150 fuel to operational squadrons in mid-1940 required careful management. For pilots, the transition meant learning new procedures as manifold pressure limits were raised significantly higher. Where a Merlin engine running Grade 130 was limited to 67 inches of mercury, the new limit was higher. The same engine running Grade 150 could safely operate at 75 inches or higher, providing massive power. Pilots had to manage fuel consumption in new ways because running at maximum boost consumed fuel rapidly. Escort missions from England to Berlin already pushed the Mustang's range to its limits even without the extra power draw. Using the new fuel's full capability meant knowing precisely when to use maximum power and when to throttle back. Ground crews faced their own unique set of challenges, as the high tetratel lead content made the new fuel significantly more hazardous to handle daily. Personnel wore heavy protective equipment when fueling aircraft, and spills work leaned up immediately to prevent the very real danger of lead poisoning. Yet the aircraft required absolutely no mechanical modifications, as the Packard Merle and fuel systems were fully compatible with both fuel grades right away. Combat reports from the summer and fall of 1940 documented the transformation, as fighter groups reported dramatically higher victory ratios. German fighters that had previously made fast, lashing attacks and escaped now found themselves totally unable to outrun the pursuing American Mustangs. The speed advantage that had once allowed them to disengage at will had evaporated completely, leaving them exposed and vulnerable to American guns. The psychological effect on Luftwaffe pilots was devastating, as they confronted fighters with seemingly unlimited performance margins day after day. Their tactical options narrowed to almost nothing, so they could attempt mass attacks or simply refuse combat entirely in a desperate bid to survive. Or they could engage and likely be shot down by Mustangs that were faster and flown by pilots who grew increasingly confident with every mission. Reichsmarschall Herm, and Göring commander of the Luftwaffe, made a famous remark upon seeing long-range P-51 Mustangs flying over Berlin. "When I saw those Mustangs over the capital," he reportedly said, "I knew the war was lost," acknowledging the inevitable defeat. Luftwaffe Technical Intelligence eventually obtained samples of Allied Grade 150 fuel from captured dropped tanks and wrecks. German chemists analyzed these samples with growing alarm, as tests confirmed exactly what their pilots had been reporting to them. The Americans had developed a fuel with performance characteristics far beyond anything German plants could ever hope to produce. Then came the bombers in May 1944, as the 8th Air Force launched a concentrated offensive against synthetic fuel. The raids on the Ruhr, one of the largest synthetic fuel plants in Germany, were particularly devastating to the Nazi war effort. Hundreds of heavy bombers struck the facility repeatedly while repair crews worked frantically, but attacks came faster than repairs. By late 1940, the Luftwaffe was rationing fuel severely, and even fighter units operated under strict constraints. Training for new pilots was cut back drastically, sometimes to just 30 hours before operational assignment to the front lines. American pilots typically had several hundred hours, creating a vicious cycle where inexperienced Germans fought highly trained Americans. Between January and May 1940, American bombers suffered loss rates of 3 to 6% per mission. Between June and December 1944, after Grade 150 introduction, bomber loss rates dropped to under 2%. P-51 groups claimed approximately 4,900 German aircraft destroyed in air combat by May 1945. On June 6, 1940, the greatest amphibious invasion in history landed with force on the beaches of Normandy. In a stunning display of weakness, only 2 Luftwaffe aircraft appeared over those beaches on D-Day to oppose the invasion. Just 2 aircraft against an invasion force of nearly 7,000 vessels and over 160,000 troops. The German Air Force had been beaten so thoroughly it could not contest the most important military operation of the war. By early 1945, Allied fighters flew multiple missions, daily limited only by pilot fatigue and aircraft maintenance. German fighters often sat grounded for lack of fuel, and when they did fly, strict conservation measures limited combat capability. A German pilot who burned too much fuel might not make it back to base, turning every mission into a calculated risk of survival. Total Allied production likely exceeded 200 million gallons, with each gallon representing an extraordinary chain of industrial activity. Crude oil from Texas and Oklahoma was refined, blended, and shipped across the submarine infested Atlantic to reach the frontline airfields. April 1945, American fighters ranged across Germany, almost unopposed on missions that had once been deadly gauntlets. The Luftwaffe was finished destroyed by attrition, fuel shortages, and systematical elimination of experienced pilots over the years. On May 8, 1945, Germany surrendered unconditionally, and the air war ended with absolute air supremacy. This supremacy had many causes, including the Mustang's revolutionary long-range excellent pilot training and overwhelming numerical superiority. Strategic bombing of German industry was vital, but among these factors often overlooked in popular histories was grade 150 fuel. This chemical advantage gave Allied fighters a performance edge that German technology could not match and industry could not replicate. Speed matters in aerial combat because a faster fighter can choose when to engage and when to escape from a fight. A faster fighter can pursue retreating enemies and break off from unfavorable encounters, giving the pilot total tactical control. A faster fighter has tactical flexibility that slower opponents simply lack, allowing them to dictate the terms of engagement. When American fighters became faster through superior fuel chemistry, the Luftwaffe's tactical options evaporated completely. The story of grade 150 fuel is ultimately about industrial warfare and the invisible supply chains that win wars. The Second World War was not decided solely by heroic pilots or brilliant generals, but by logistics and production capacity. It was decided by nations that could produce more aircraft, superior fueling, overwhelming numbers of well-trained pilots. Germany possessed brilliant designers and courageous pilots, but Germany could not match American industrial capacity. Germany could not produce high-octane fuel in sufficient quantities, nor could they train pilots thoroughly to replace losses. In the end, the Luftwaffe was buried under an avalanche of American production that simply never stopped coming. Fighters that were individually excellent were overwhelmed by superior numbers swarming the skies like locusts. Pilots who were individually courageous were worn down by endless combat until they could fight no more. And somewhere in all of this, a German pilot named Gunter Schack belly landed his crippled Messerschmitt and watched it burn. He wondered for 4 decades how an American Mustang closed so fast, and the answer was always in the fuel. If you want more hardcore breakdowns of history, deadliest miscalculation, smash that like button and subscribe. I am your strategy observer.